Welcome. Today, we're diving into the world of vibe coding, a term for coding with the help of AI prompts, sometimes with little traditional programming knowledge. As AI coding agents become seamlessly integrated into our development environments, it's tempting to believe that prompts alone can build robust software. But is it really that simple? We'll explore the benefits, the pitfalls, and the essential techniques every coder, novice, or expert should know to make the most of AI-assisted development. Let's start by understanding what vibe coding is and why it's become so popular in modern software engineering. AI is rapidly becoming an essential part of the coding workflow. Integrated into IDEs, AI agents can generate code, suggest improvements, and even help debug. This shift is changing how both experienced developers and newcomers approach software creation. While AI can accelerate prototyping and proof-of-concept work, relying solely on prompts without understanding the underlying systems can be risky. The key is to use AI as a powerful tool, not a replacement for foundational knowledge. In this scene, we'll look at how AI fits into the daily routine of modern developers and why understanding its limitations is crucial. It's not possible or necessary to know everything about programming. However, what separates effective developers from the rest is their awareness of their own knowledge gaps. This self-awareness allows them to ask the right questions, seek the right help, and use AI tools more effectively. For vibe coders, especially those new to the field, recognizing what you don't know is the first step toward building reliable and maintainable software. In this segment, we'll discuss why humility and curiosity are vital traits for anyone leveraging AI in coding. Software isn't static. Unlike a statue, it constantly evolves, features are added, bugs are fixed, and security holes are patched. This dynamic nature means that software must be designed for change. Software construction techniques, such as modular design and abstraction, help manage complexity and make future modifications safer and easier. In this scene, we'll introduce the core idea behind these techniques, tackling complexity by introducing abstractions in data types and function calls. These methods are the backbone of maintainable, extensible software. Object-oriented programming, or OOP, is a foundational paradigm in software construction. It introduces concepts like encapsulation, protecting the internal state of objects, and polymorphism, which allows behaviors to be extended without duplicating code. The idea of data abstraction, championed by Barbara Liskov, underpins OOP. Classes represent types with attributes and methods bundled together. Inheritance and dynamic binding allow for code reuse and flexibility. While OOP has evolved and some languages have moved away from it, its core principles still influence modern software design. One of the most important ideas in software design is the open-closed principle. It states that software should be open for extension but closed for modification. In practice, this means you should add new functionality by extending existing code, not by changing what already works. For example, instead of modifying a stable class, you create a subclass for new features. This approach minimizes the risk of introducing bugs into working systems and makes your code base more robust over time. Let's see how this principle guides safer, more maintainable development. Not all modern languages support inheritance directly. Languages like Go use interfaces and composition instead. The key is to achieve extensibility, adding new features without changing existing code regardless of the language. By understanding your language's tools, you can apply the open-closed principle in any environment. When using AI, it's important to prompt for solutions that fit your language's paradigm, ensuring your code remains flexible and maintainable. While it's important to design for extensibility, overdesign can be just as harmful as underdesign. The goal is to strike a balance. Design enough to avoid frequent, risky modifications to working code, but not so much that the system becomes overly complex. AI can help suggest improvements, but it's up to the developer to judge when a design is sufficient. In this scene, we'll discuss how to avoid both extremes and keep your codebase healthy. AI can help you check if your code follows solid principles, especially the single responsibility and open-closed principles. By crafting the right prompts, you can ask AI to suggest ways to restructure your code for better extensibility and maintainability without adding unnecessary complexity. For example, you might prompt, "Does this code follow solid principles, especially the single responsibility and open-closed principles?" Suggest how it can be restructured to improve extensibility and maintainability. This approach leverages AI's strengths while keeping you in control of the design. Most of a software system's life is spent in maintenance, not initial development. Good maintainability practices like structured logging, summary counters, and clear comments make it easier to debug, extend, and support code over time. AI can help by suggesting where to add logs or how to improve readability. For example, you might prompt, "Improve the maintainability of this code." Add structured logging at key points, include summary counters, and ensure readability. These small steps can make a big difference in the long run. Security is a critical concern in any software project. AI can help identify common vulnerabilities, such as SQL injection or cross-site scripting. But it's up to the developer to prompt for these checks and review the results. For example, you might ask, "Please review this code for SQL injection, XSS, and other OWASP top 10 issues." While AI is powerful, it's not infallible. Secondary reviews and a solid understanding of security best practices are still essential, especially for critical systems. Test-driven development, or TDD, is a powerful approach to catching bugs early and ensuring your code is reliable. With TDD, you write tests before you write the code itself, making sure every feature is covered from the start. AI can help generate both code and tests, but it's important to understand the logic and intent behind each test. By prompting AI to write diverse unit tests, including edge cases and invalid inputs, you can catch subtle bugs that might otherwise slip through. TDD keeps your codebase robust and testable. AI can be a great ally in generating unit tests for your functions. By asking for a mix of typical use cases, edge cases, and invalid inputs, you ensure your code is thoroughly tested. For example, you might prompt, "Write 5 well-structured unit tests for the following function." Cover a mix of typical use cases, edge cases, and invalid inputs. Documenting the intent of each test helps clarify what scenarios are covered and why. This practice not only improves code quality but also helps you understand the code better. So, are prompts all you need? Not quite. As Euclid famously said, "There is no royal road to geometry." The same applies to software engineering. While AI and prompts can accelerate learning and development, there's no substitute for deep understanding and real-world experience. The more you know, the more you can leverage AI effectively. College, work experience, and continuous learning remain essential for mastering the craft of software construction. No matter how advanced AI becomes, real-world experience remains irreplaceable. Only by working on real projects do you learn to handle ambiguity, debug tricky issues, and appreciate the nuances of software engineering. From chasing memory leaks to dealing with complex bugs, these lessons shape you into a better developer. AI can help you learn faster and avoid common mistakes, but the wisdom gained from hands-on experience is what truly sets great programmers apart. The future will need both experienced and new programmers, each bringing unique strengths to the table.